Example 16.9. In this example, we have a thin metal plate which is insulated on the back and exposed to solar radiation on the front surface. The exposed surface of the plate has an absorptivity of 0.6 for solar radiation. If the solar radiation is incident on the plate at a rate of 700 watts per meter square and the surrounding air temperature is equal to 25 Celsius. We need to determine the surface temperature of the plate when the heat lost by convection and radiation equals the solar energy absorbed by the plate. We assume the combined convection and radiation heat transfer coefficient to be 50 watts per meter square Kelvin. So the main part in this problem is that the absorbed amount of heat transfer per unit area is equal to the amount of heat combined between radiation and convection, also by surface area. So let's start by calculating what is this quantity, the amount of heat that is being absorbed per unit area. That is simply equal to the amount of absorptivity times the value of the heat transfer incident over surface area. So we have that to be simply 0.6 times 700 watts per meter square, and we find that to be 420 watts per meter square. So the amount of combined heat transfer between radiation and convection is simply the combined heat transfer coefficient times Ts minus T surrounding. Notice that these two values are equal to each other, so we could make this also equal to 420 watts per meter square. Now we solve this equation for Ts. So we simply find that Ts is simply going to be the 420 watts meter square divided by the amount of the heat transfer coefficient, of the combined heat transfer coefficient, which is 50 watts m square Kelvin, plus the surrounding temperature. And solving for Ts, we find that to be 33.4 Celsius. So notice that the result does make sense. The amount of the surface temperature is higher than the surrounding air temperature. And once again, we do this problem by doing a balance of energy between the amount of energy absorbed, the heat transfer absorbed per unit area, and the combination of both the radiation and convection. Because it is combined, we simply multiply by a delta. Therefore, there is no difference whether we use delta Kelvin or delta Celsius, as long as we do delta only.